Swayam Prabha. Digital India. Educated India.
Good morning everybody. Today we will be discussing a very important vacuum gauge or two gauges which are quite popular and quite rugged and which are routinely being used in process industries. Process industries, semiconductor, ultra high vacuum, they are also process, but most of the time process industries means chemical, pharmaceutical, food, etc. And the semiconductor chip manufacturing, etc., they are more called as high-tech manufacturing industries or electronic industries like that, metallurgical industries. It's a sort of generic name, but otherwise everything is a process by itself. Whatever happens in molecular level, we normally call it as little high-tech, and this one is in viscous level or semi-viscous level or transition regions, etc. So, there are gauges for poor vacuum, medium vacuum, high vacuum and ultra high vacuum. That is one aspect. As we have seen in the last class, when we are discussing U-tube manometer and McLeod gauge, we were talking about primary and secondary gauges. Primary is they directly respond to the force or pressure. In fact, there is nothing very clear definition. There are certain gauges which are also quite fundamental, like a mechanical deflection. If you are very careful, you can reliably do it a rugged way. So, in a way that can be also primary. So, the thing that I am going to talk today, like capacitance gauge, it is a measurement of capacitance. In a way it is secondary, but it is so rugged and reliable and reproducible, it acts like a secondary standard in the lab scale. So that you need not always go to McLeod gauge or U-tube manometer, mercury handling, all that, and take that to the laboratories, etc. These are quite rugged and reliable and stay in that rugged condition for a longer time. So, you can keep some of these good gauges in the lab, and once in a while you can calibrate your other gauges, which I am going to discuss next week, like thermal conductivity gauges or ionization gauges, etc. You can use these gauges to sort of standardize or calibrate within the lab scale, but it is not a perfect calibration. So, that way capacitance gauge is also in a way can be called primary. Forget about primary, secondary or anything. Certain gauges are very accurate according to the definition or fundamentals. Certain gauges are very simple to look at and inexpensive, and you can get a display in using electronics. They are more friendly. Friendly people may not be very accurate. Okay. So, accurate things are different. Accuracy requires a lot of standards, etc. For example, pressure gauge calibration, vacuum calibration, all these things are done in every country in national laboratories, National Physical Laboratory, NIST is there in US, they look after vacuum standards and all. The way they measure the vacuum level is in a very sophisticated way. Okay. So, you have to take your gauges there, and there is a lot of procedure, and it will take quite a long time, and without any background error they will give very accurate values. But in most of the processes it is not that much required to measure exactly 3 into minus 4 or 3.5 into minus 4. Display will keep on coming down, but that does not mean at that instant of time that is the vacuum. This is what I want you to understand when we are discussing pressure measurement, because later I may not get time to discuss these points. In a big chamber, when pressure gauge is somewhere and pump is somewhere, and in semi-molecular phase like minus 2 tar or minus 1 tar, where mean free path is just of the order of the distances between two solid substances, solid surfaces, then what happens is there may be some pressure differences within the chamber. And what you are measuring, by the time you measure, already it has gone down in a dynamically very high speed. evacuation, for example, load lock chambers in a semiconductor industry. You may not have enough time to measure the pressure. They are only interested in getting the final pressure, okay, respectable, repeatable pressure. So, it's more of a indication of the order of the vacuum. For such people, it is the response time that is very important, that it is going down like that. McLeod gauge and all, you will have a lot of slow response time, because you need to collect, you need to compress, etc. So, secondary gauges are also very much essential in process industries, very high speed dynamic measurement. But now and then you have to calibrate them. You cannot say I am going to measure inaccurately, that is not allowed. In fact, most of the gauge manufacturers, I do not say all of them, they themselves are not sure whether their gauges are giving with this much accuracy. You ask them, just what is the accuracy, can I get it after 3 months, same thing. They will say it will give more or less same order, sir, and you need to have calibration, sir, and ours is reproducible, our display is very good, it is computer interfaceable. They will never say the starting sensing point, the physics behind it is absolutely reliable. So, vacuum measurement, if somebody says I am measuring very accurately, he is fooling. It is not possible very accurately. High pressures may be possible little, because it is in a continuum range. It behaves like a gas. Boyle's law is very accurate to even 0.1, 0.01%, because it is tested if you know how to maintain a temperature constant. But at lower side, it is more of a statistical thing, molecular phenomena. How can you say the pressure is constant, or at this instant of time, this is the pressure, my sensing time constant may be different, the actual pressure fluctuations may be different, even there is a process going on inside, then that will disturb the vacuum level. So, varieties of problems you need to understand. Well, again when we discuss applications and system design, we will come back to this, but just I want you to understand accurate measurement is not that much possible, not that much required in day to day life. Very rarely it is required, but not always. And today one vacuum level, tomorrow we are depositing same level, that is important. Relative accuracy is different. I do not know whether that measurement is accurate or not, but today and tomorrow same measurement. So, if that x is 10%, tomorrow also if x is there, that also may be 10% error with respect to absolute standards, but relative accuracies are different. All these points many people are not aware in vacuum technology. I want you to understand these things, because there are lots of transformations by the time you get the display, from the sensing, then temperature, then resistance, relating it to molecular density, relating it to pressure. It needs continuous research. In fact, even today very few people all over the world are working on this. Initial days there was a lot of work, but everybody uses vacuum, everybody wants to measure accurately, everybody says high tech process, clean process, vacuum. But if you ask them about measurement, they will say it is a small thing, we measured with a gauge, that is all. Who made that gauge, whether that was accurate, nobody knows. Okay. So, reliability or ruggedness is different, because you can rely on that gauge that every day that much pressure it is coming, you can start the process. But whether that is accurate or not, accuracy is different. Okay. With this introduction, I will not bore you much. Let us go to these two gauges, because we have to complete the syllabus. So, we will see Bourdon gauge and capacitance gauge today. Why I have clubbed these two gauges? Both of them depend on mechanical deflection to the forces created by pressure differences. In a way, primary forces, pressure differences, but they are not as accurate as U-tube manometer or McLeod gauge, because they are defined with respect to millimeter of mercury, that itself is the unit. So, in a way slightly different standards in a way, but these are also quite good rugged gauges. So, in the concepts that we are going to discuss in this lecture are Bourdon gauge, capacitance gauge, their working principles, and some idea about their limitations. Whether you should believe it with full confidence or not, you should be little careful. But if they are used as control sensors to switch on some relay or some other process, open that wall, this wall, then relative accuracy wise these are very good gauges. but they are expensive. Capacitance gauge is little expensive. Bourdon gauge is very cheap, available. In fact, Bourdon gauge is mostly used in high pressures in refrigeration industries, even in cylinder pressure, all of them, they are called dial gauges. But actually the principle is more or less same. That we will see now, because Bourdon has discovered it. So, both the vacuum as well as high pressure gauges, they use Bourdon tube. What is that Bourdon tube? How it is related to a linkage of the pointer? It is well known in the Wikipedia. I am not going to give you fundamental knowledge of maths and mechanical engineering aspect of it, nor we are interested in this vacuum technology course. But a brief idea I will be giving. Capacitance gauge also requires electronic instrumentations, how it is going to measure accurately, how it can be kept as a secondary standard in a laboratory, that also we will see. Okay. So, these two concepts we will cover, and next class onwards we will cover purely secondary gauges. This is a transition between primary to secondary. Purely secondary gauges are thermal conductivity based gauges like Pirani thermocouple gauge, then ionization based gauges like hot cathode ionization gauge, cold cathode penning gauge, inverted magnetron gauge, etc. Again there is a sort of fundamental principle related molecular drag type of principle, that is also one gauge is there at a high vacuum side, spinning rotor gauge. In a way it is fundamental, but the amount of instrumentation required to make that sophistication, that is very costly. So, that also we will touch upon as a sort of standard under high vacuum conditions. Okay. That we will see in the next few classes. So, this class we will concentrate on Bourdon gauge and capacitance gauge. Bourdon gauge first is a very simple gauge, it is a good old gauge. This type of dial gauges you must be observing everywhere in day to day life, in kitchen also you may have, and in several gas networks or industrial networks or gas cylinders or process chambers, everywhere you will find dial gauges. Slightly difference is that side it is measuring with respect to atmosphere higher side, here we are going to measure with respect to atmosphere lower side. Again I will remind you that there is nothing called negative pressure. Most of the time, since the gauge pressure is measured with respect to atmospheric pressure, we will think that 0.1 psa or 1 psa means what? 14.5 psa absolute pressure of atmosphere plus 0.1 or 1. So, when you are using fundamental equations like PV, nRT, etc., you cannot use this 0.1 or 1, you have to use absolute units. Okay. You should be careful, like centigrade is okay for friendliness, but when you are using it in thermodynamics, you have to use in Kelvin. In fact, most of the people make mistakes and end up in wrong design. So, people who are dealing with this process application, they should be aware of these elementary things which look elementary, but if you miss, it can be fatal. Okay. So, you should be very careful. Bourdon gauge is very rugged and very inexpensive, because this is an extension of already developed pressure gauge. Okay. And it can be permanently mounted. There is no electricity requirement, there is no fluid requirement, mercury requirement or any such thing, and there is no glass material. It is a rugged piece. It is like voltmeter or current meter. You can just hook it up to any point with a necessary coupling and tighten it and leave it there. No problem. If for example, refrigeration compressors, etc., you will have these gauges. And when you carefully observe refrigeration network, you will find plus side that measures the freon pressure, but the minus side also it will be there. Normally, we will never get that indicator, but during the maintenance, they will evacuate and refilling, that time the signal shows minus. That is, the minus means what? With respect to atmosphere, it is minus. During that time, it is a vacuum gauge. But if you are using purely vacuum gauge, our maximum point itself is 1000 millibar absolute. So, this Bourdon gauge that I am showing you in the figure is a pure vacuum gauge. Its upper limit is 1000 millibar. To be on safe side, if there is a pressure fluctuations, you can create little more that side also, so that suddenly pressure goes, gauge will not get spoiled. Okay. But there are also gauges both plus side and minus side half of things. They are also very rough gauges. You cannot measure very accurately in such a small scale. Whether it is 40 tar or 42 tar, impossible. But graduations are every 20 tar. So, with your eye, what you can measure? So, all these things should be kept in mind, but quite rugged. Ruggedness on one side and inexpensive is another side, and requirement of special fluids, the third side, electricity requirement, all these things. And reproducibility is different, accuracy is different, sensitivity is different. These things you know by now in class which has been studied. If there is small change in pressure, will it show? Again, sensitivity. And is it measuring accurately what it is supposed to be? That is accuracy. Relative means control sensors. One process you have done and calibrated that level, that process is working, you are sure. So, every time you bring to that level, what is that level, we are not worried. That is a relative accuracy. Okay. So, you have to be careful in process applications. Why I am talking like this is, when these gauges are used in process application, because the whole subject is on vacuum technology and process application, you have to understand which gauge to rely under what situations. Unnecessarily, you should not use very sophisticated gauge when pressure can be measured plus or minus 10%, 20%. It is just a suction of a vacuum cleaner. How does it matter? Or a distillation column, or a very drying chamber, etc. You are not that much worried because huge amount of loads are coming, anyway fluctuations are happening. Just you need to have a suction force. So, that time these Bourdon gauges are extremely useful. You do not need to spend any extra money, and they will not get easily spoiled. Quite a good mechanically strong gauge. And it is used in rough vacuum systems and permanently mounted local gauge. So, maybe up to 10 millibar with a lot of accuracy you can do it. Below that it is not possible. We will see what are the limitations little later. First, let us try to understand construction and action of it. As the name itself says, it includes a Bourdon tube. Bourdon tube is nothing but a thin walled metal pipe, which material and a lot of research is going on even now, and an elliptical cross section. Why elliptical? A lot of work is there, that force balances, etc. I am not going to deal with that, it will take 10 hours. Okay? An elliptical cross section, and one side closed, the other side connected to the system whose vacuum we are measuring now, and high pressure people say whose pressure they will be measuring. For us, vacuum. So, it contains a tube, metallic tube, in cross section wise. That means, if you take this at any point, the cross section will be elliptical, but as a whole the tube is bent in the form of a letter C, and one side it is closed, the other side it is connected through a suitable couplings and threaded joint, and it will be finally coupled to either pipe or chamber to the vacuum system whose vacuum we are measuring. And this entire thing is arranged with a pointer arrangement with linkages, etc., which are finally coupled to the closed end of it. If this end moves, this will move accordingly, and this pointer will be rotating on the circular scale. So, there will be a small scale. You can prepare in your lab, take a paper and make some, this one, you take another lever or make some pin and other things, you can make it as a sort of exercise in a mechanical engineering department. In fact, we have made a thermal conductivity gauge like that in a B.Tech project, and it works because fundamental principles are same, but a company does very nice looking things, no? That is so different. So, the cross section is elliptical at any section, the overall tube will look like a C, and it is made out of a elliptical cross section and a thin walled pipe. So, outer surface is exposed to the local pressure, atmospheric pressure, because there is no leak tightness here, and inner surface of this C tube is exposed to the vacuum. So, if you keep any surface element, outer side there will be high pressure, inner side it is a vacuum. So, that is how the C, atmospheric pressure initially we are starting. So, as the vacuum is getting developed, then what will happen? It will start getting deflected. Because of pressure differences on outer area and smaller area, that will be converted again in the circular way, and there are a lot of equations to explain how this force will be acting on this and all. I am not going to show that. So, these deflections are finally measured and calibrated using a primary sensor like U-tube manometer in fixed points. Then you can use it left and right very rugged way. Okay. The resulting difference between outer and inner is the fundamental principle, and that will be coupled to the linkage and a circular motion, there will be scale. This is the constructional aspect of it. So, what is the action? An increase in the pressure will give you opposite effect, with the curved element opening slightly indicating rise in pressure. Okay. Whereas, if it is vacuum, the deflection will be curling in, the otherwise it will be curling out. Okay. This C coupling. This is well understood, there is nothing great about it, it is a simple mechanical gauge. Now, one important point, suppose the local pressure itself is different. If you go to Mount Everest, then outer surface is also little partial vacuum, then deflections will be different. So, you have to have some barometer in the local level, correct that in this reading, either reading wise or some zero adjustment of this gauge. These are done routinely with some additional facilities in by manufacturers. So, that has to be done using local barometric pressure corrections. This is one important aspect of it. Okay. So, finally, Bourdon gauge is an extension of high pressure gauge. The relative motion of this C, whether curling in or curling out, it is just the opposite effect, depending on whether outer pressure is more or inner pressure is more, you will get opposite effect. Is that clear to you? Okay. So, more than this, if you want to understand exactly how to make, you have to see the Wikipedia, and anybody can have a startup with this and see whether you will get proper readings and with local gauges, and you can sell it, no problem. And a mechanical engineer can easily make mass production. All that you require is some tubes, some couplings, some bit of heat treatment, so that it will act like a springiness will be there, and that all that you have to adjust it and make a reliable thing and good looking things. Okay. So, calibration is of course required for this. Okay. After this mechanical measurement, nowadays people want everything display. I want electronic things. I don't have time. Okay. I am in a software company or in a electronics company or some other high-tech company, and I just want to see everything digital display. Once digital things are there, I know how to process the signals, how to do that. Digital process system, all are well developed nowadays, digital technology. So, electronic way of measuring is becoming more and more popular. So, deflections, how to convert them electronically? One of it is through capacitance manometer. This is also basically deflection manometer like other C tube type Bourdon gauge, but it gives a signal instead of an indicator in the Bourdon gauge, mechanical indicator with a coupling. Here it gives a signal. How? You can read, I am not going to read this. This is a small pillbox type thing, a small circular box having two chambers separated by a thin diaphragm. That will be also circular plate, and under tension it is braced inside. Technology is quite involved. It is not as easy as I am talking. You have to do it very carefully. And one side a floating electrode is kept here with an electrical insulator, which is connected to this metal again using metal to ceramic joint. So, this is one pneumatic chamber, this is another pneumatic chamber, and this is connected to the pressure to be measured. This is to be connected to the reference, but instead of connecting to a reference pressure, you can seal it and with a local pump, getter pump. We have discussed already adsorption pump, etc. No? Chemical getter if you keep. Once you evacuate, you can seal it somewhere, and afterwards a local pump will take care to maintain vacuum in this chamber, perfect vacuum. This vacuum should be much better vacuum to the measuring range of the vacuums that we are talking in this chamber, where the pipe is connected to the system. So, this pipe is connected to the vacuum system whose vacuum we are measuring. So, this will be varying from 1000, 100, 10, 1, minus 1 like that. Below minus 2, minus 3, the deflections are not that accurate. So, they can be worked with great difficulty up to minus 3, minus 4. Okay. So, this diaphragm will be looking at a difference in pressure on both sides. Naturally, this is almost 0 pressure compared to this, because it is maintained at high, ultra high vacuum, and if there may be some spurious leaks or degassing inside, which can be taken care by this locally sitting small chemical pump called adsorption pump. There is no rotary pump or anything here, because the whole gauge itself is a small piece, and inside we are going to have a small getter, okay? And this getter will be able to absorb those gases. And when you do that, under this P2 minus P1, and P1 is almost 0 with respect to this, because 10 power minus 4 is a 0 compared to 1 or 10, etc. So, P2 minus P1 is nothing but P2, which is your vacuum to be measured. So, this is absolute pressure gauge, this is a differential pressure gauge. That is with respect to mechanical aspects. So, electronic aspect is, if it gets deflected, which side it will go? The diaphragm will bend this side, because this side is high pressure. When it bends, the gap between this fixed electrode and metal diaphragm, which itself is a grounded plate, it will act like another electrode. And the distance between two plates of a capacitor, if it changes, what will happen? Epsilon naught A by D, etc. All those equations are taught in school. So, capacitance changes. Okay. Once capacitance changes, then you can use this capacitance change in a tank circuit or suitable circuit, where you can convert into frequency. 1 by 2 pi root LC we have studied in class 12. So, this fixed electrode and this variable electrode diaphragm, which bends based on the pressure value, local pressure value, it can be 100 millibar, it can be 1000 millibar maximum, and 1 millibar. Different ranges will have different things. You will not use one diaphragm for the entire range, maybe 1000 to 100 one capacitance gauge, 100 to 10, 10 to 1, several manufacturers manufacture these things. So, depending on the deflection, the local capacitance changes. That capacitance is picked up by a suitable electronic circuit. This is a typical commercial appearance of capacitance gauge. This is a Pfeiffer gauge. They manufacture quite a good number of gauges, which are there in our lab also. There are many other companies who manufacture these capacitance gauges. In fact, in India, we do not have a good manufacturer of gauges, because I know most of them. They are trying their best, but a standard vacuum measurement requires very careful instrumentation knowledge and material science knowledge and vacuum knowledge. So, if anybody wants to have a startup on this manufacturing reliable with a little bit of standardization or calibration, it will be very rugged and it can be dependable gauge. You will have a very big market, particularly when semiconductor industries are coming up in a big way in India, pharmaceutical is coming, chemical industries are coming. So many things are coming, but x-axis, who measures the pressure accurately and inexpensively? So, you have to develop these gauges in-house. So, I will be very happy if somebody is interested after this course. If you want to come, you can approach me. We can, I can suggest you how to go about it. Because idea of this course is to make you self-sufficient, because this is a Swayam course. You can take from anywhere, and based on that knowledge, you will start developing these things for our national purpose. Okay? So, this is an absolute pressure measurement with differential pressure, one side being 0 and sealed off things, and capacitance will be converted into frequency. Why frequency? If frequency is one thing which can be measured in 1 in 10 power 8, 10 power 9, super heterodyne principle, etc. It's gigahertz, for example, microwave frequency. You can measure up to 1 hertz That is why microwave frequencies are given for cell phone and all this. Each customer will have one particular frequency, next customer will have another frequency, slightly different. Bandwidth should be so high, but individual frequencies will be only in the 9th digit or 8th digit small changes. So, there will be inlet filters and how to select these things, that is an electronic thing. We will see when we at some other application time when we are discussing cell phones etc., the role of vacuum there later. Okay. If you do all that, frequency can be measured accurately and that frequency will be suitably connected through a proper converter circuits, and finally with a little bit of amplifiers you can convert into a display units, and display we will start getting the actual pressure. But backside what is happening is, first display is nothing but some converted signal, that signal is proportional to some frequency, that frequency is proportional to capacitance changes are proportional to deflection changes are proportional to the pressure changes, a vacuum range changes from 1000 to 1 millibar at 10 power minus 1 millibar across a diaphragm, other side being perfect vacuum maintained by a getter pump. So, I am talking little faster, but you can slowly understand, and because these gauges are very popular nowadays, they are acting like a secondary standards. They can stand little bit of chemical environment. Okay. All thermal conductivity gauges and all which we are going to discuss later, if they get oxidized filament, it will not work properly. Similarly, ionization gauges, if it suddenly some exposure of air, wire gets cut, then the entire thing has to be thrown. Here no such thing will happen. Suddenly, inadvertently you suddenly open atmosphere, nothing will really happen to this. There will be cut off in the electronic side and diaphragm gauge will not get deflected. Okay. Because little bit of oxide layer will not change the natural deflection frequency or natural deflection of a diaphragm. It is a little bit of 0.1 millimeter. So, another 0.1 millimeter change does not matter. But if it is a ionization gauge, then it changes, surface matters. Here the mechanical strength matters. All these points you have to slowly understand, and when to use this gauge, all that. And with accurate experiments can be done with this gauge. You can measure roughly up to 10 power minus 4 to minus 5 torr. They can use it to calibrate some other digital gauges like Pirani gauge etc., by connecting two gauges with a T-arm connected to a chamber, put a needle wall and put a pump. By compensating inlet of this some gas and exhaust by a pump, you can stabilize different things. Whether it is stable or not, gauge will show. That accurately we are not measuring, but it will show that reading is not changing because we have a display electronically. That can be calibrated with a McLeod gauge. So, that way you can calibrate those things. That we will see in the calibration procedures in the next class. And SCADA can be used to give this signal from this capacitance, whatever that comes out, analog signals, you can give it to some controllers, and process can be controlled in chemical or pharmaceutical processes etc. These are very important. I do not bother to use gauge only for the measurement sake. I will also use it to control some other process, to open some valve in a process industry. Okay. And it should be very fast. In a load lock chamber in a semiconductor industry, load the wafer and immediately do some cleaning operations etc., and immediately transfer it to the main chamber for growth chambers. But during this time, very fast you have to data log that it has come to that pressure. So, there these things are rugged and useful. Certain things may be faster, but they may not be rugged. Thermocouple gauge or Pirani gauge, after some time they will measure something else, they are not reproducible. That way this gauge has got its own merits. Okay. But of course, nothing comes free of cost, it will be little expensive. So, that is why I am again telling it is the perfect case for any startup fellows to take it up, make it inexpensive and use it in a mass production. Nowadays, lots of control circuits are available, like you can use any of those things, A to D converter, frequency converter, all of them are available nowadays. So, you can add some instrumentation knowledge with these things and make a beautiful display and nice looking gauge. Gauge, actually we call gauge, but actually in the real sense it is called gauge head, that is the sensing element type. Gauge is the place where you are trying to see the value as a display, but we normally call it as vacuum gauge. So, all these things have become habits over a period of time, but scientifically you have to know the roots properly. Okay. And at higher pressures also you can use little thicker materials. Higher the pressures, forces will be different, you can afford to use thicker things. Okay. If you use very thin, it may get punctured or something. You have to be very careful. But temperature should be constant. If you make some measurement, after some time pressure has changed, but actually pressure might not have changed, because temperature has changed, some deflection may change. So, you should see to that all the pressure range throughout the process experiment that you are doing, temperature should be maintained constant. That sort of things are available also in instrumentation. Even if temperature is not constant, some other sensor will measure temperature, and temperature compensation can be done electronically now. So, this is a smart sensors today. So, that is why sensors have got lot of things inside. That sort of instrumentation with mechanical things, with suitable metallurgical processes, making a diaphragm and understanding the natural deflections, all that if you do, you have a very good business, and this is very important for day-to-day applications. Most important is semiconducting applications and medium pressures. So, with these things, with temperature compensations, etc., most of the problems are solved, and these gauges can be used as a primary gauges are comfortable gauges if you can afford to spend money, otherwise they can be used as a standard gauges. So, with this we have completed deflection type of gauges, both Bourdon and capacitance gauges. In the next class we will start now the secondary standards, first thermal conductivity, then ionization, etc. Thank you very much.